Hi, wishing you all. I'm Dr. Jeguri, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about some definitions which is in the module crystal structures. So, in the last sessions, we have seen some of the definitions. And today, we will see about some definitions, that is unit cell, what is lattice parameters, remaining and all. So first we shall see the review of bases. So in the last session we have been discussed about the basis. Basis is a group of atoms or molecules attached with each lattice point to give a real crystal. So basis is a group of atoms or molecules attached with each lattice point to give a real crystal. So in this, the crystal structure will be formed by associating the lattice and basis. Crystal structure is formed by associating lattice and basis. So here the crystal structure is a real one and this lattice is an imaginary concept. And this basis is a group of atoms. So by forming these two, we'll get that real structure, that is a complete crystal. So here in this diagram, here we took that lattice and lattice plus basis. So here the basis is group of atoms. So if we take NaCl as an example, this NaCl belongs to Na, this one is Cl. So when it is associated with the lattice, when this basis is associated with the lattice, then we'll get the complete structure of the crystal. Complete structure of the crystal. So the complete structure will be, you can see that here at the place of each lattice point, so each lattice point, lattice is nothing but representation of atoms in a space or plane. Okay, so here lattice point means that each point on the lattice called as lattice point. So each point on the lattice is called lattice point. Okay, so here it represents an atom. So but here when taking lattice, we are taking at the place of atoms, we are representing with a point. So at each place of a lattice point, we are showing that here a group of atoms, that is basis. At each lattice point, it is associated with the basis. So that's why, so the complete structure will be as like this. Okay, so if we take NaCl, that NaCl crystals will be at each lattice point. So I will show. So this is NaCl cubic crystal. The structure of this NaCl. So at each corner we have a lattice point. So here it is associated with a group of atoms, that is this is Na and this is Cl. Then the complete structure will be formed So the complete structure when associating with group of atoms, so it becomes, so NaCl is associating with the lattice point, NaCl, like that every place at a lattice point it is associated with group of atoms. So then the complete structure of the crystal is formed. Then complete crystal structure of sodium chloride is formed. So this is how the crystal structure is forms. Next, coming to the unit cell. The unit cell is the smallest volume of a solid. The unit cell is the smallest volume of a solid or geometric figure from which entire crystal is built up by translational repetition in three dimension. In three dimension. So the unit cell is the smallest volume of a solid which the entire crystal is built up by translational repetition in the three dimensions. So it also, that is this also fundamental, this also called as a fundamental elementary pattern of a crystal because it repeated again and again to form the lattice structure of a crystal. So it is also known as fundamental elementary pattern of a crystal because it repeated again and again to form the lattice structure of a crystal. So simply, unit cell is a smallest part. Unit cell is a smallest part of a plane or space which can be construct entire crystal by translational repetition. So simply, a unit cell is a smallest part of a plane or space that is which can be construct entire crystal by translational repetition. Translational repetition means that so it in the linear way. Translational repetition. If we suppose if we take this is an unit cell, so this would be like this. The unit cell is translationally repeated so that this crystal structure is formed. Crystal structure is formed. So unit cell is the smallest part. So this one is the smallest part. So in this plane or in this plane lattice, this is the smallest part. This is the smallest part. So through which it is constructed the entire crystal by translational repetition. By translational repetition. Translation means in linear way. So linear way, it is repeated again and again. The unit cell is repeated again and again so that the complete crystal will be formed. So here we can see that this we can see that 3D in space. This is a space lattice. In space lattice, the smallest part of this solid is this. So this is the smallest part in this complete solid. So this part can be written here separately. So this part alone is called as unit cell. This part alone is called as unit cell. So by repeating this unit cell, we can build up the entire crystal so that the crystal structure forms. So here in the same way, this unit cell is repeated again here. Here it is repeated. So this is again it is repeated. This is unit cell 1 and this is unit cell 2. Like that linear way it is repeated and repeated. Here also we can see that. So again and again it is repeating. This is another block. Like that complete crystal is formed. In this way we can see here. So in this way we can see here like this. So like this in linear way the unit cell is repeated again and again so that the complete structure will be formed. So coming to the lattice parameters. Coming to the lattice parameters. So the lines drawn parallel to the lines of intersection of any three faces of the unit cell which do not lie in the same plane are called crystallographic axis. So in this lattice parameters we are seeing about the crystallographic axis, what are the crystallographic axis and what are the interfacial angles, then we'll go for the lattice parameters. So first we shall know about the crystallographic axis. So the lines drawn parallel to the lines of intersection of any three faces of the unit cell which do not lie in the same plane are called crystallographic axis. So the angles between three crystallographic axes are known as interfacial angles or interaxial angles. The angles between the three crystallographic axes are known as crystal sorry interfacial angles or interaxial angles. So the length of the unit cell along x, y, and z directions are a, b, and c. We are assuming that the length of the unit cell along the x, y, and z direction. Then we can uh, draw the lattice parameters like this. That is, here this is a sodium chloride crystal which is in 3 dimension, and here a small part of the crystal of sodium chloride, that is in this crystal a small part, that is unit cell is this one. Here it is noted. This one. So here A, B, C. A, B, C or the length of the unit cell. So the length of the unit cell along X, Y, Z directions are A, B, C. X, Y, Z. So along X direction, the length is A. Along Y direction, the length is B. Along Z direction, the length is C. So the angle between the axis x and y, the angle between x and y is equals to alpha. Let's see in this diagram. Here the crystallographic axis are x, y, z. From the diagram, the crystallographic axis are x, y, and z. Here the angle between the axis, that is x, y. So the angle between x and y is alpha. Is alpha. The angle between y and z. The angle between y and z is beta. The angle between the axis z and x. Angle between z and x is gamma. Angle between x and z is gamma. So the intercepts A, B, C defines the dimensions of an unit cell and are known as its primitives or characteristic intercepts on the axis. So this A, B, C. So the intercepts of A, B, C defines the dimensions of a unit cell. It defines the dimensions of the unit cell. So these A, B, C are called as a primitives. This A, B, C are called as a primitives, or else we can call it as characteristic intercepts on the axis. Characteristic intercepts on the axis. So these three quantities A, B, C are also called the fundamental translational vectors. Fundamental translational vectors. So these three, that is A, B, C, which gives the length on the axis of a unit cell. So this A, B, C defines the dimensions. Defines the dimensions of a unit cell. A, B, C defines the dimensions of a unit cell. These were called as primitives or characteristic intercepts on the axis, or as these three quantities called as fundamental translational vectors. Fundamental translational vectors. So here the angle between the crystallographic axis and these primitives collectively called as lattice parameters. So A, B, C, alpha, beta and gamma are collectively known as lattice parameters. Lattice parameters. So ABC defines the dimensions of an unit cell, and alpha, beta, gamma gives the angles between the crystallographic axis. So completely called as lattice parameters. What is primitive cell? What is primitive cell? So the unit cell formed by the primitives. So the primitives are A, B, C. Primitives are A, B, C. So these A, B, C are the representation of the length of an unit cell on the crystallographic axis. So interceptions are also can gives the intercepts on the crystallographic axis. So the unit cell formed by the primitives A, B and C is called primitive cell. Is called primitive cell. So in a primitive cell, there is only one lattice point. In the primitive cell, there is only one lattice point. If there is more than one lattice point, then it is not a lattice point. It is not a primitive cell. It is not a primitive cell. So here from this diagram, we can see the lattice. In this lattice, there are lattice points. So lattice points. So in the lattice points, there is a small part of solid, that is smallest volume is this one, here this one. So here So one point is which are formed with primitives. Primitive cell is nothing but a unit cell which are formed with primitives. Unit cell formed with primitives, and it should have only one lattice point. Then only we call as primitive. So a unit cell is formed with primitives and it has only one lattice point. Then we call as a primitive cell. Here in this diagram, this is a primitive. So why we are saying this is a primitive unit cell? Why it is not a non-primitive? Why it is non-primitive unit cell? Why it is non-primitive unit cell? In this first one, suppose this may be unit cell 1 or this may be unit cell 2. Unit cell 2. So here there is 4 lattice points. So 4 lattice points, connecting to a 4 lattice points, a small unit cell is formed. So this lattice points can be shared to other 4 unit cells, so that each lattice points can be shared to other 4 unit cells. So that suppose if we take a unit cell, so if we take this unit cell, then this is the smallest part of the unit cell. This is the smallest part of the unit cell. So here at each corner there is a lattice point. So each lattice point at the corner, each lattice point at the corner can be shared with other 4 lattice points of the other unit cells. So this can be shared to the other lattice point, unit cell. So this is shared with other unit cell, and here this lattice point is shared with the other lattice point of the other unit cell. So like that, each corner lattice point can be shared with other unit cells, so that at each corner it is there is a shared lattice point, that is 1/4 atom or 1/4 lattice point be there in this unit cell. So 1/4 of an atom into 4 corners is equals to 1. So only one lattice point we are getting here. So I'm taking a lattice, so plain lattice. So in this, a smallest unit cell is formed with combining the 4 lattice points. So this 4 lattice point is shared with other 4 lattice, that is other 4 unit cells. So this lattice point is shared with other 4, which is upside, which is backside, which is the besides like that, this each atom at the corner, each atom at the corner be shared with other unit cells, so that each corner only one fourth atom or one fourth lattice point only be there in this unit cell. Okay, so that one fourth atom into four corners is equals to 1. So we are getting only one atom, totally one atom or one lattice point. In the representation of lattice, we say one lattice point. One lattice point is nothing but one atom. So we are getting only one atom. That is only one lattice point. So lattice point is 1. Okay, in this unit cell. Coming to the other one, unit cell 2, this unit cell is connected, that is it is also a smallest part in this plane lattice. This is unit cell 2 also a smallest part in the plane lattice, and it is also connected for lattice points. But comparing to the unit cell 1, there is one more lattice point which is at the middle of this unit cell 2. There is one more lattice point which is at the middle of this unit cell. So when calculating total number of lattice points, as like in the unit cell 1, so four corner atoms is shared with other four unit cells, so that one fourth atom is there. So one fourth atom into four corners is equals to, this is for unit cell 2. So one lattice point, and at the middle of the unit cell, there is one lattice point. So totally 1 plus 1 is equals to 2. So we are getting 2 lattice points in this unit cell 2. So our condition is only one lattice, the unit cell which is formed with primitives and has only one lattice, then it is a primitive cell. But in unit cell 1, we are getting only one lattice point totally. But here in unit cell 2, along with the corner atoms, there is one more atom being there here at the middle of the unit cell. So 1 plus 1, we are getting lattice points, 2 lattice points. Getting 2 lattice points here. So that it is non-primitive. It is non-primitive. So in this session, we have seen about unit cell and what are the interfacial angles, what are the crystallographic axis, and what about the lattice parameters. Then we have seen the primitive cell, and in this primitive cell, we have clearly with the diagram have been discussed how the primitive cells can be formed, how it is primitive, and how the other one is non-primitive. And so in the next session, we shall see about the Bravais lattice. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.